How fast is this ball moving? To answer this question, we could use the speed equation, distance over time. Here, the ball travels about 400 centimeters in about 5 seconds. After plugging in our values, we get a speed of 80 centimeters per second. But there's a small problem. This ball clearly does not travel 80 centimeters per second throughout the entire trip. It can't. I mean, if the ball was traveling 80 centimeters per second consistently, it would never stop moving. Since it does come to a stop, it must slow down. 80 centimeters per second is only the average speed of the ball. Instead of finding the ball's average speed, how could I find the ball's speed at just a single moment in time? It's instantaneous speed. Let's try graphing the situation. The ball's journey can be modeled by a distance function. Any value of time you input into the function will tell you the distance the ball has traveled after that amount of time has passed. What we're looking for is a speed function. This will tell us the speed of the ball at any time value we input into it. The speed function is what we call the derivative of the distance function. It gives us an instantaneous rate of change. Of course, the idea of trying to find speed at a single moment or an instantaneous rate of change doesn't really make a whole lot of sense. For there to be a rate of change, there has to be, well, some kind of change, and when you limit yourself to just one point in time, there's not really much room for change. This is the same conflict that the founders of calculus dealt with, and their solution was actually pretty clever. If I wanted to find the speed at a single point, let's say t equals 3, but I need 2 points in order to compute speed, how about I just use 2 points really close together like t equals 3 and t equals 3.1? If we were to use these t values in the speed equation, it would give us a really good approximation of the speed at t equals 3. The smaller delta t is, the more accurate the approximation. So if I made delta t equal to 0.001, then plug this into the speed equation, this would give us a really great approximation for the speed at t equals 3, or at any other t value. Now this right here is almost what a derivative is, but we are still missing one piece of the puzzle: limits. Without limits, our equation is only an approximation for instantaneous speed. The magic of calculus is making approximations exact through limits. The derivative is not the ratio of delta s over delta t for a specific value of delta t, such as 0.001, but rather, it is what this ratio approaches as delta t approaches 0.